Let's put those principles into practice with the function for example 2. We'll find the second derivative and evaluate it when x equals 2 and y equals 1. We found the first derivative of the function in example 2. Remember, it's often easier to find the second derivative if we start from the expanded form like this, rather than the form where we have y prime on the left-hand side and all the x's and y's on the right-hand side. We'll differentiate with respect to x term by term. We'll start with the first term. It's a product, 3y squared times y prime. So we'll use the product rule. First we need to differentiate 3y squared with respect to x. We'll use the chain rule. We'll let z equal 3y squared. That implies dz dy is equal to 6y. dz dx equals dz dy times dy dx. That's equal to 6y times dy dx, remember, is y prime times y prime. Now we can go on and differentiate 3y squared times y prime. d dx of 3y squared times y prime. We apply the product rule. It's equal to, we have the derivative of the first part, 3y squared. That's 6y times y prime, that in brackets, times y prime, plus 3y squared times, well, the derivative of y prime is y prime prime, the second derivative. That's equal to 6y times y prime squared, which is different to y prime prime, plus 3y squared times y prime prime. Our next term is 6xy. We'll differentiate that, and then we'll go on and differentiate 3x squared times y prime. d dx of 6xy. We have another product there. The first part of the product rule will be 6 times the derivative of x, which is 1, times y, so it'll be 6y, plus 6x times y prime. The last term is 3x squared times y prime. Again, we'll use the product rule. Differentiating 3x squared, it'll be 6x times y prime plus 3x squared times y prime prime. Putting all that together, we'll have 6y times y prime squared plus 3y squared times y prime prime plus 6y plus 12xy prime. We have 6xy prime there and 6xy prime there. That gives us 12xy prime plus 3x squared times y prime prime equals 0. We could collect the y prime primes. Y prime prime times 3 times x squared plus y squared plus 6y plus 6y y prime squared plus 12xy is equal to 0. We want to evaluate the second derivative at the point 2, 1. We could substitute in here. We have values of x and y. We know what the first derivative is. We can find a value for that at point 2, 1, and then solve for y prime prime. This is an example from the textbook, and that's the way they do it. There's not much of a challenge in that, though, is there? Let's see if we can find an explicit form for y prime prime. We can subtract 6y times y prime squared plus 12xy from both sides. Our next step is to divide through by 3 times x squared plus y squared. In this case, as we'll see, it's simpler to treat each of the 3 terms on the right-hand side separately. We can cancel out the 3's in each term. Next, we want to substitute in for y prime. We have y prime here and here. That implies that y prime prime is equal to, the first term is the same, minus 2y minus 2y on x squared plus y squared times y prime squared. That will be minus 2xy all squared in the numerator over x squared plus y squared all squared minus 4x on x squared plus y squared times y prime minus 2xy over x squared plus y squared. We can simplify that. We need to be careful. We have a minus sign here, but it's squared, and another minus sign here. Y prime prime is equal to minus 2y on x squared plus y squared. We end up with a minus sign here because the minus 2xy was squared. 8x squared times y cubed in the numerator over x squared plus y squared all cubed plus minus 8x squared y divided by x squared plus y squared all squared. Now we have an explicit function for y prime prime. We want to evaluate y prime prime at the point 2, 1. Substituting in for x and y, we'll have y prime prime is equal to minus 2 on 5 minus 8 times 4 times 1 on 5 cubed plus 8 times 4 times 1 on 5 squared. We can do that calculation and we get 78 on 125.